Earth-like planets are very hard to detect because the effects that they have on their central stars are very low, and most of the detection methods that we have rely on the detection of these effects, gravitational or light exploration effects, transit effects. So with respect to the exoplanet types that have been detected so far, and I should point out that this number, or these numbers, continue to change. Since we now know almost 2,000 extrasolar planets, their numbers continue to increase. With respect to these numbers, we know mainly huge gas giants of Jupiter size or even more massive objects. We know also quite a few less massive gas and ice planets, more the size of Neptune, for instance. We know quite a few rocky planets that are, however, much more massive than Earth. These are the so-called super-Terran planets or super-Earth planets. Earth-sized planets, for these we only have a very small number, and even less massive objects, their numbers are yet again smaller. Probably this does not reflect the true distribution of planetary masses. It's probably more a reflection of our bias of our detection methods, which favor the detection of these massive objects over here. And an interesting question that always comes up then is, of course, well, could some of these planets harbor life? Maybe even life as we know it, or maybe it would be life that is completely different from the life that we know. When I say that we know now of approximately 2,000 planets, these numbers continue to increase. There are estimates of how many planets our Milky Way might have or other galaxies might have. And according to these estimates, every star has on average 1.6 planets. If you calculate then the number of stars in our Milky Way, you end up with estimates for our Milky Way alone of more than 100 billion planets. And at that point you might ask the question, could some of these planets also have conditions that favor the evolution of life and possibly carry life? Whether it's intelligent life is a completely different question. It might be very simple life, more along the lines of bacteria. But of course, that's a very interesting speculation. At the moment, it is indeed pure speculation, since we have no way of detecting that. There are different options of how we could try to address this question. For instance, in our solar system, we can send probes to other planets to look for traces of life, and those planets of which we think that they might potentially be conducive to the formation of life, like Mars, or possibly moons of more distant gas giants like Jupiter and Saturn. On these moons, we actually find also atmospheres. These are very massive moons. The question has been raised whether there also life might have formed. Overall, there's the concept of the so-called habitable zone. Habitable zone refers to that region across a central star within which planetary systems might actually experience conditions that are conducive for the formation of life. Now, what exactly is necessary for the formation of life? We don't really know. We just judge from life on Earth. For life on Earth, one vital condition is the presence of an atmosphere and the presence of liquid water. Liquid water is a major compound of the cells in our body. All the reactions in our cells rely on the presence of liquid in these cells. And water is a very versatile element. It's a very common element, a very simple element composed of some of the most commonly occurring elements in the universe. Another important element would be carbon. Our life is carbon-based. All life on Earth is carbon-based. It always consists of cells containing carbon. So these ideas about habitable zones usually are based on life on Earth. Whether there could be completely different life is a separate question that we cannot yet answer. And the habitable zone refers to that region within which planets could potentially have conditions under which liquid water could exist on their surfaces. This regime, or this range of distances, depends on the type of the central star. For more massive stars, we would have a different regime than for low-mass stars. And you basically see a plot in which different stellar types are indicated, and then various of the extrasolar planets are indicated, as well as known planets like the ones in our solar system. This refers to a sun-like star. Here we have less massive cooler stars, here we have hotter stars, and here we have the regime in which potentially life might exist. Basically this region here, over here probably we have greenhouse effects that would potentially prevent the formation of life. Over here the conditions might be too icy. So with respect to that, we could ask which of the so far detected extrasolar planets could actually be conducive to the existence of life. Again, this is highly speculative. Well, people have tried to define a so-called Earth similarity index in order to define this in a little bit more detail. And basically, this Earth similarity index is a function of the radius of the extrasolar planets, the density, the escape velocity, which would then allow, for instance, an atmosphere to remain on that object, and the surface temperature, which allows the formation of, or the retention of liquid water on its surface. So again, everything here is based on life as we know it, and of course maybe a fairly biased view. And within this regime, we find, of course, Earth as an Earth similarity index of 1. Any Earth similarity index less than 1 means that we are moving away from the conditions of Earth. Mars is still within the regime where maybe life might have existed at some point, but it already has a much lower index. Mercury and Venus are basically inhospitable as we know today. And of course, gas planets and ice planets would be excluded from this. So with respect to that, among these roughly 2,000 planets, these are the planets that remain as potentially having conditions that might allow for the formation of life. Again, I have to emphasize this is quite speculative. We have no way of testing that directly. These planets are all far too distant for us to send probes there. In some cases, we can hope through a variety of different techniques to get an idea of their composition by looking at their atmospheres. There's something called transit spectroscopy that allows us, under certain favorable conditions, to get some idea of the outer atmospheric composition, allowing us to look for traces of life, such as ozone. But again, that is quite speculative. So there are a few planets, at least extrasolar planets, that might be habitable, that might have conditions conducive to life.
做个总结好了哈，这个系外行星现在刚才讲到已经发现了2000个左右，其中有1000个已经是确定的，因为造成系外行星观察现象的不一定是系外行星。在这1000个里面，大家做出来的统计就是每一颗恒星平均有1.6颗行星，所以天文学又改写了。以前我们研究恒星的人，恒星很多嘛，行星就这么8个，对不对？你做来做去没什么可以做。不是的，系外行星完全改观。这边他介绍一个概念叫做 Earth Similarity Index， 有多像地球。我们很在乎在这些系外行星里面有哪些它的环境是很接近地球的。不管是我们在那边发现独立诞生出来的生命，或者我们要移民过去另外一个家乡，对吧？另下一个地球，都跟这个有关。这边基本上讲的就是大于0.9的没有。目前我没有找到一个跟地球非常非常像，就怎么判断它的距离、它的母恒星的大小啊，它自己质量的大小啊，能不能因此就有温度的大小，可不可以有大气层啊等等，这都是未来我相信在10年、25年之内会有长足进展的一个行业。
With that, basically, I'm at the end of my talk. We started out with cosmology. We moved all the way to planets. By the way, these planets here on this side are just shown for comparison. These are solar system planets, obviously. These potentially habitable planets are all super-Earths, much more massive than Earth. What we do not know is whether they actually contain an atmosphere like Earth, what the composition of the atmosphere is, and so on and so forth. There are many, many unknowns here still. But I would just like to come to my concluding remarks. I try to demonstrate here that our universe has undergone an extremely complex evolution, beginning with events that happened on extremely short time scales, like the formation of fundamental particles, pair productions, fractions of seconds after the Big Bang, to structure formation happening on much longer time scales. And then I went on to the formation of galaxies and finally stars, which may last basically billions and billions of years. Then I finally talked a little bit about planets. The formation of the evolution of the universe is not yet completed. The evolution of the universe is continuing. We are actually just at a certain evolutionary stage. We really live in a very dynamical world that continues to experience changes, that continues to evolve. And astronomy has basically a very wide scope. It tries to look at all of these different processes in a wide range of different scales and a wide range of different times also. Depending on the subject area, astronomers explore, for instance, questions related to the solar system itself, to extrasolar planets, to star formation and stellar evolution, to galaxy formation and evolution, cosmology, and so forth. There's a wide range of different topics that one can explore in astronomy. And many important questions remain unresolved. The nature of dark matter, about which I didn't talk much more, whether there is, in fact, other life in the universe. Some of these answers may well revolutionize our picture of the world, may change our worldview quite considerably. Basically, it's really a fascinating journey that is still continuing and that will undoubtedly